Well, I think we can start, if you all agree.
Okay, yes. Okay, thank you for inviting us to this presentation. It's our pleasure to share with you my research or our research topic. Let's start Mouna to introduce herself first.
Well, I would like to thank you guys as well for this invitation. Now, for introducing myself, well, my name is Mouna Keltoum Benabid. I studied for 5 years petroleum geophysics in the Faculty of Hydrocarbons and Chemistry, University of Boumerdès here in Nigeria. Then I graduated last year. I have been recruited within Schlumberger to work as a field engineer, a testing field engineer. And now I'm a PhD candidate in the University of North Dakota.
Thank you, Mouna. My name is Abdulaziz Ellafi, PhD candidate at University of North Dakota. Also, I am working as a research assistant at Energy and Environmental Research Center, ERC, as a reservoir engineer. Let's start with our presentation for today. The topic is experiences from advanced technology in hydraulic fracturing treatment in unconventional resources. In this presentation, we will add challenges, success, and lessons learned. In this presentation, we will go through over unconventional resources and specifically talk in details about Bakken petroleum system. We add problem statement in terms of oil recovery and environmental issues. Then we go through water management options. We finalize this part by experimental and simulation studies. Then Mouna, she will talk more about microseismic and geothermal resources.
Yes.
For unconventional resources, is classified by the characterization with low permeability and porosity compared with conventional formation. It's the term of the shale is not typically that shale in lithology, but it has poor quality formation. We need to have high technology to produce from unconventional resources using hydraulic fracturing, but we need to consider to have in commercial way and consider the environmental to have better design without any environmental issues. More for unconventional resources in the United States, like Bakken in North Dakota, Eagle Ford, Premium Basin and Barnett in Texas, and Marcellus in West Virginia and Pennsylvania. Once started the revolution in unconventional resources in 2010, the shared volume of production compared to the total production, it was just 16%. Then jumped up to 60% in recently once we have recovered in oil prices. And petroleum experts expected that the production will be increased up to 70% to 80% in next few years from unconventional resources. This depends about how development in technology, also the oil price, since this unconventional resources need more technology to produce it with low cost. Two competitive shale plays in the United States are Eagle Ford and Bakken petroleum system. The production is around 2 million barrels per day before the prices drop. This made the United States as an independent energy country. Outside of the United States, there are opportunities in other countries like in North Africa and Middle East, in both for tight oil and tight gas. One of our research study, we try to transfer the technology that have it here in the United States to these resources to check the opportunities and what are the challenges to produce more hydrocarbon from these resources. Let's talk about Bakken petroleum system here in North Dakota, which is in Williston Basin, is the shared area between North Dakota, Montana, and Saskatchewan in Canada. The formation consists of 3 layers. upper and lower are source rock with high TOC value. And the middle one is hybrid formation between conventional and unconventional formation. Once we check the quality of the formation is better than upper and lower and permeability in micro size, we need to drill with our target for drilling horizontal well in the middle Bakken to produce more hydrocarbon. Before we go to the main hydraulic fracture design, we go through the diagnostic fracture injection test. The main objective of this mini frac to get idea about the formation, to collect some data that can be used in the design, like fracture closure pressure, which is minimum horizontal pressure, horizontal stress. This can be used, this data, for main hydraulic fracturing design to have better design. And the injection fracture diagnosis test is around 5 to 10 minutes using short or small volume of fracture fluid. We prefer to use the same fracture fluid for the main design. Then we shut in the pump to record the pressure versus time, which this is fall-off period. From fall-off period is divided to 2 stages. First one is before closure, that fracture dominated flow. From there we can know the fracture half length, we know the closure behavior and leak-off coefficients. After that, once the fracture closed, the flow transfer to the main formation. From there we can obtain reservoir permeability and average reservoir pressure. The length of fall-off period, this depends about the quality of the formation. Once we have like tight formation, we need to take, might be up to 7 to 8 or 10 days recording the fall-off period. If the formation it has good, better quality, I think in 1 or 2 days we can reach the radial flow. We analyze these data using a G-function plot. This is created by Nalty and Smith. From the G-function plot, we can analyze before closure analysis to obtain the closure behavior and the closure pressure. Then we can move to the main hydraulic fracturing. In main hydraulic fracturing design, we go with the first stage, is bad stage. Just we injecting fracture fluid under high pressure to create the fractures. And here the example of the middle Bakken. One of the common fracture fluid that used in the industry today is friction reducer. The friction reducer has low friction loss through the pipes and better proppant transport. After the bad stage, we go with the slurry stage. We inject fracture fluid with the proppant. The objective of the proppant is to keep the fractures open after we shut in the pump. Also, using friction reducer can have better performance, can transport the proppant to the tip to the fractures to create higher SRV volume. Once we have higher SRV volume, we can produce more hydrocarbon. We have 2 ways. Either we consider the conductivity or the fracture half length. This depends about the formation. Like the example for Houston, this Houston is Highway 10 is very busy. We can classify it as a conventional reservoir. We have better permeability. We can produce more hydrocarbon from that. That we don't need to consider the fracture half length. We need to consider the conductivity rather than fracture half length. That once we apply the design, we rely on the conductivity than fracture half length. Another picture, it's highway in Libyan desert. There is low population. We don't need to create wide highway. We need to consider fracture half length, the tall one. This represents the unconventional formation. The fracture fluid consists of mainly of water. They use it fresh water. The percentage is 99%, with sand, which is the proppant. The rest is additives, depends about the formation, about the application that we need to use, and commonly now using friction reducer. And we can also use scale inhibitor or surfactant or other type of additives. The trend for fracturing fluid started with using cross-linked and linear gel, silk water, and now friction reducer. Why friction reducer? Because we have perfect proben transport, low damage, and one of the important things is low cost. Since the friction reducer is type of polymers from its nature, come from agricultures, it can be used, firstly use it as a drilling fluids, then now apply it as a fracture fluid. Once we compare between conventional fracture fluid and unconventional fracture fluid, like high viscosity friction reducer, we see how the proben transport and better fracture half-length can be created. Why we need to study more about hydraulic fracturing and to perform better design? Since the well performance for unconventional wells, the age is around 3 to 5 years. They starting the production with the peaks, then we have sharp decline in the production. And the reason of the sharp decline is the depletion in natural fracture and twisted fracture near the SRV volume. Without any support beyond the SRV, we need to create better design to have better stabilization in the plateau for like time frame. Then we can go to either using refracturing or using enhanced oil recovery CO2. Other problem statement that face our operators in the United States today, it is using consumption of the fresh water. As you can see from the map, there is in each shale play we have different consumptions in water, fresh water, and this fresh water comes from rivers and lakes and can be used more for agriculture and livestock. Once we compare other unconventional resources out of the United States, like in the Middle East, there is limited resources of the fresh water that we need to figure out other resources can be used with the fracture fluid to create hydraulic fracturing. In the same time, the operator faces the increase in the oil production or increase in the water production instead of oil production. It is the percentage is 10 barrels instead versus 3 barrels of oil. We need to figure out the solution for water management instead to throw the water in the surface and make like environmental issues, serious environmental issues. The characterization for reduced water, it has high TDS, and here from the map show that in Bakken formation it has higher TDS compared with other shale plays. Also, it has other element from reduced water like sulfide, chloride. This make a challenge to use it again with the fracture fluid. For water management options, there are different options using conventional way by filtration, using filter papers, or using vaporization. And both these methods can cost a lot of money and need facility in the oil field to use it. Other option, they use it also, they re-inject produced water in shallow formation. But this can cause a problem since the pressure can propagate and make a failure in casing for nearby wells, or go to the other formation like shallow grounded aquifer and make water contaminations. Halliburton come up with solution. They using electrochemical process for water management, for flowback and produced water to separate organic and inorganic material without change the elements for the solution or the TTS. and they use linear gel and high viscosity friction reducer with this process and show better result. One of other why we need to use produced water with the fracture fluid, since fresh water, it has cost a lot of money. There are another costs related to the transportation. Once we talk about transportation, we can consider other environmental issue, which is the air contaminations. Also, water waste, it can cost a lot of money. Once we consider today the oil price, it's low, up to $40 by barrel. This can accumulate a lot of cost. That's why we need to find the solution reusing the produced water instead using other storage options. Why we study Bakken petroleum system? Since there is a lot of opportunities here in North Dakota. One of them in Montreal County. In Montreal County, the permeability and the formation characterization is better. It has better quality. We can use it for refracturing, design, and CO2 EUR application. And most of our research study, it is in Montreal County. We go with the survey first for the lithology or mineralogy for middle Bakken formation, and the results show that it has high amount of clay and quartz. On the other hand, the produced water in Montreal County also show higher amount of TDS and different elements like iron and chloride and sulfide. This makes it challenge to use it with produced water, again with fracture fluid. And here for fracture fluid, we focus just on high viscosity friction reducer. It's classified to 3 types: non-ionic, ionic, and cationic. The more popular one is cationic, since it has it doesn't has any limited with TDS value. But when we back with the mineralogy of middle Bakken characterization, we show it has a high amount of clay. And the reaction between cationic fracture fluid and the clay can make swelling. Then we can make the scenario is worse. We reduce the permeability. That's why we come up using non-ionic polymer. We need to enhance it by different options. Before we select the fracture fluid, we need to go with the rheology characterization using rheometer to know about the viscosity profile. From viscosity profile, we have higher shear rate and lower shear rate. Higher shear rate represents the injecting the fluid from the surface, but the lower shear rate represents the shear rate inside the fractures, and we are just interested in the inside the fractures, since the main objective of the fracture fluid is not just creating fracture, is transporting the proppant from near wellbore to the tip of the fracture to keep it open and create high SRV volume. Then we have higher surface volume. We can produce more hydrocarbon. Other test is very important is elasticity test. From the elastic test, we know that this type of proppant has better proppant transport or not. We gather these results from the lab, then we can use it for reservoir simulation using different type of reservoir simulation, hydraulic fracturing, to know how the propagation of the fracture geometry will be. The solution to enhancing non-ionic high viscosity friction reducer, we're using surfactant. The surfactant can expand the chains from the polymers instead of the cutting the chains. Once we expand these chains, we can have better viscosity and elasticity. Also, they found that once we use surfactant, we can reduce the friction loss through the pipes. Once we talk about the friction loss, that means we don't need higher horsepower in the service. And this also related to the cost. As we know, the surfactant, it has other terms that for oil and gas industry can change the wettability. Once we use surfactant with fracture fluids, then we can have better performance of proppant transport as well as better oil production. Here in UND lab, we take the samples from field, from Montreal counties using reduced water. At the first time, we need to go with the filtration process to take the organic and organic material. We come up with the solution using dilution process with different percent of reduced water and tap water, which is fresh water. And after that, we study the rheology using different type of loading process. The first, once we create the fracture fluid, we have makeup fluid, which is reduced water diluted with fresh water. Then we add fracture fluids, which is high viscosity friction reducer. This is called dosage or loading. We go with 0.25 to up 8 GBT loading. We study the rheology in different temperatures to check which type or which load can be tolerate the high TDS value. And from the rheology process, we see this fracture fluids can save 15% of fresh waters. We can increase the dosage or the loading of fracture fluid to reduce the amount of fresh water. One of the reasons why we increase the dosage to have better viscosity, since this fluid is environmental, it doesn't cause any problem to the formation and it has low cost. Once we gather all the data from the lab, we use real field data to have implementation test. We couple this with reservoir simulation and fracturing simulation. We use ray transit analysis as a tool for investigation or diagnostic once we have better fracture have length or not. We mimic the behavior from the field data using reservoir simulation. Then we come up with different scenario with different type of fracture fluids using RTA to detect the effective fracture have length. And finally, we're using different type of fracture fluid. As you can see from this plot, surfactant can tolerate the high TDS, create better distribution of proppant, and better conductivity and fracture have length. And the final result showed that from reservoir simulation, surfactant with high viscosity friction reducer can able to produce more hydrocarbon. As I mentioned, that's the role of the surfactant with high viscosity friction reducer is not just tolerate high TDS to create better SRB volume, but to change the wettability of the formation to produce more hydrocarbon. Then now Mouna can start for the real-time monitoring of hydraulic fracturing. Go ahead, Mouna.
Thank you for your presentation, Aziz. Well, guys, for me, it's gonna be a presentation about microseismic as a very powerful tool monitoring the hydraulic frac. Okay, so I know, I believe you guys are not geophysicists, most of you at least, but I will be trying to explain things in a very simple way so we can, at least at the end of this presentation, we will understand all the basics and then the basic principle behind microseismic, and we will be able to ask, let's say, the most relevant questions and appropriate ones regarding this technology. Okay, Now, as Aziz mentioned, hydraulic frac nowadays is being a wonderful technology, okay? Since it's allowing us to recover oil and gas from reservoirs, unconventional reservoirs that we couldn't imagine one day we will be able to produce them and at a commercially very economic rates, right? Now, the question is, do we need to monitor these operation, like the hydraulic frac? Do we need to monitor it? And let's say the main question is why? What's the why behind monitoring these technology? Can you just go to the next slide, please, Aziz? Well, actually, because let's just imagine we are fracking our reservoir, guys, and let's just imagine that those fractures are actually developing into a depleted zone, right? Or it can be simply developing into out of our target. But the worst case scenario is just like when you have your fractures developing into, let's say, a water bearing zone or the shallowest aquifers, like Aziz mentioned it. And at this moment, we do have a real environmental issue, right? We are contaminating our water. That's why we really need to monitor the hydraulic fracking system into the reservoir. Now, please, the next slide, Aziz, as well. Now, what if we could have a tool allowing us to monitor those fractures, okay? What if we could have at real time, and by real time, I mean at the same time the hydraulic frac operation is being done by the stimulation engineer, what if we could have at that moment a tool allowing us to visualize those fractures and then getting the description of its geometry, right? Then at that moment, we could be able to do decisions in order to better manage our reservoir in terms like technically and hence economically. We could save costs, right? And at the same moment, we are lowering the risk of the environmental issues, right? Nice. Well, that technology and that tool for today is going to be microseismic, okay? And we are actually talking about the microseismic being a very powerful tool since, Aziz, the next slide, please. It does actually exist many of the bunch of other methods that can allow us getting a description of our fractures, right? Just like pressure transient analysis or analysis of the production rates and so on. Like there is a lot of methods. But for any method, at least, we do have one or two variables that remain unclear, which is not the case for the microseismic. Like for microseismic, the positive point, let's say, or the powerful point here is the fact that we can have the full description of the geometry of our fracture. We can have its length, its width, and its height, and its orientation, okay? And that's for the space, for the 3D space domain. At the same time, we can have its development into time. That means, let's say that we are doing a fracking operation, and at this moment, which is T0, we are acquiring microseismic data, okay? We do have the geometry of our fracture at T0. We will be doing the same after 1 hour, and for sure, the fracture is not going to be the same in terms of geometry, right? So the fracture is developing, and in function of time, we are getting at each time the geometry. Then we do have a fourth dimension, which is time, okay? So we do have a very powerful 4D, let's say, method to monitor our fractures, okay? Nice. Now, the question actually is, how is microseismic allowing us getting those information? How does like the microseismic help us predicting exactly the fracture, its length, its width, its height, its full geometry, okay? Now, you guys know that in the reservoir formation, we do have plans of weaknesses, right? So when we just go through the hydraulically frac the rock, slippage for sure and tensile deformation will occur, okay? And that weakness point will just break down. At that breakdown, it's gonna send a seismic energy, okay? Sounds logical, right? So that energy will propagate through the subsurface, and in microseismic, we will be recording that that energy, that seismic energy, okay? So to do so, for the acquisition design, we just implement an array of receivers in a well that we call an observation well, okay? It's gonna be a well near to the treatment well. So we just implement the array of the geophones, the seismic receivers, and we gather that seismic energy. We gather that seismic data, okay? Now, let's just zoom in and try to understand how do we get from that seismic data the location of the fractures, okay? Aziz, please, the next slide. Thank you. So you guys can see the point, the orange point, which we are considering it microseismic event. Okay, that's a microseismic event. That's the breakdown point, let's say, from where the seismic energy is coming. Okay, so there will be a seismic energy that will travel directly and be straight forward to the receiver and will be gathered there. Okay, so at the receiver, we're actually recording the arrival time. Sounds logical, right? We are recording the arrival time of this seismic energy. It means the arrival time of our P and S waves, the seismic waves simply, okay? We do have a seismic wave coming from point A, which is the microseismic event, to the point B, which is our receiver. We do have its arrival time, okay? Now, by using the famous mathematical equation, the simplest one, the relationship in between velocity, time, and distance, we do have the velocity model of our subsurface. Okay, we do have the velocity model of the P waves subsurface. Okay, and we do have as well the arriving times of the waves. We will be using time and velocity to simply extract the distance, right? Then we do have the location of the microseismic event. We will be using as well for the azimuth the particle motion of our waves, the way it's hitting our receiver. We will use the particle motion to extract the azimuth. Okay. Now we're actually gonna go through each microseismic event, gather it. Okay. And can you just go to the next one, Aziz, please? The points you can see, guys, are all microseismic events that we tried to extract their location, and it just appeared like it's appearing like a cloud, right? Then we use that cloud to extract the full geometry of our fracking system. This is to explain as simple as possible the microseismic as a technology monitoring hydraulic frac. And then as a last slide, we wanted just to mention that. Can you go to it, please, Aziz? We just wanted to mention that the hydraulic frac as a technology is not only limited to the oil and gas reservoirs, right? We do have hydraulic fracking and unconventional reservoirs for geothermal systems, and at the same way we are using the microseismic as a method to monitor it. And if you guys sounds like you really are interested by geothermal, we can have a lecture later on to talk into details about the geothermal system. At the last point, we would like to thank the NDIC and the Petroleum Engineering System in North Dakota University for their support. And thank you guys as well for your invitation and for attending the meeting. So if you guys have any questions, just go ahead.
Thank you both for your presentations.
Sorry.
If anyone have any questions, we have a time.
Hello.
Hello.
Hi. Hello.
My name is Mohammed Malki. Thank you for this presentation. Actually, I do have a question regarding the fluid for hydraulic fracturing for Abdulaziz. What if we use supercritical CO2 instead of water as fluid? I know that there is several advantages when it comes to that. For example, we can use the CO2 as storage, so we can use it for hydraulic frac, and in the same time we can use it for storage. But I believe that there are a lot of drawbacks for this new technology, like the viscosity or frictions. So what do you suggest about this technology?
Okay, thank you for your questions. I have heard about using CO2, and recently they use it for DFIT analysis. But for my research, I don't have any study about this CO2. Once, just mainly like I can, like my suggestion for the frac fluid, they mainly focus on the viscosity and rheology properties. They need frac fluid that can create fractures and have better proppant transport without any damage. Honestly, I don't have any idea about CO2, but thank you for your for adding this.
You're welcome. Thank you.
Do we have any more questions? Feel free to ask whatever you want.
Yes, sure. You guys are petroleum engineers, but need to understand from where the microseismic data and how is the geophysicist interpreting data, right? So feel free to ask questions.
Can I add something like for frac fluid or main hydraulic fracturing? Now something, one of the main completion process we need to do for developing unconventional resources. But we need to have better using this technology, as Mona mentioned, using microseismic to have less environmental issue. Then we can transfer this technology for other shale plays outside of US, like in Algeria, in Libya, and Middle East. These countries, they need to like perform hydraulic fracturing in low cost. And considering the limitations, one of the limitations is the produced water, is the fresh water. We can use this fracking fluid also can be capable with the seawater. Since it has close TDS with the produced water, it can use it as a makeup fluid to create the hydraulic fracturing.
Thank you.
I do have another question.
Yeah,
please. Regarding the effect of stress containment on the length and the geometry of the fracture. So when we have a fractured reservoir, and we don't have an anisotropy in the stress, how that can affect the geometry of the frac.
Yes, this so interesting. Okay, what Mona now doing, and for my research also, we are going to monitoring in real time. Okay, we go with stage by stage, using different tools. Like we combined all the tools to consider the effect of the stress shadow, where in which stage we have like successful implementation or we have failures. And this part of research for Mona and other part for me, and this under investigation now.
Yeah, like the possibility, how possible is it to make real-time interpretation, how is accurate getting those interpretation results and including them into the stimulation operation and then getting better results, including geomechanics and hydraulic frac and microseismic and so on.
Okay, thank you.
Welcome. Also, if anyone has
okay.
questions, can contact us by email. We are happy to answer any questions. This more valuable for us, like to improve our research. Also, can open new tasks for us for future work.
Sure.
So
Okay, then I guess.
go ahead.
Sorry. If we don't have any more questions, I guess we can finish now. And I would like to tell our students and the rest of the audience that, as they said, you can send us an email or you can contact our teachers for today, may I say so, and ask your questions freely if you're too shy to ask them now or you don't know what to ask. And I guess that will be all for today.
Yeah, thank you.
Yes,
Thank you.
Thank you very much.
Keep up the great work.
Thank you. It was very interesting.
Thank you. Have a great time. Bye-bye.
Thank you.
Thank you.
Bye.